Imagine boarding a ship headed for the nearest star. You leave everything behind, everyone you love, everything you know. The journey to Proxima Centauri would take longer than human civilization has existed. And that's before you even deal with what's waiting for you on the other side. Is any destination in the universe actually worth that? If you want to feel genuinely small and genuinely amazed on a regular basis, make sure to give this video a like. Now let's get started. Most people have a mental image of interstellar space. It's a vast, silent void, dark emptiness stretching between the stars like an ocean with no water. You drift through it peacefully, covering enormous distances, and eventually you arrive somewhere. That picture is not just incomplete, it is dangerously wrong, and understanding why it's wrong is the first step to grasping just how formidable this journey truly is. Here's something almost no popular science coverage mentions. Before you even reach the halfway point to Proxima Centauri, you are still technically inside our own solar system. Let that sit for a moment. Our sun governs a vast spherical shell of icy rocky bodies called the Oort Cloud. It begins somewhere around 2,000 astronomical units from the sun, where 1 astronomical unit is the 150 million kilometer distance between Earth and the sun, and it extends outward to somewhere between 50,000 and 100,000 astronomical units, possibly further. Converting those numbers, the outer boundary of the Oort cloud sits roughly 1 to 2 light-years from the sun. Proxima Centauri is 4.24 light-years away. That means the first light-year or more of your journey is still, by any honest definition, our solar backyard. You would be well on your way to the nearest star before you'd even escaped the sun's gravitational reach. The Oort cloud itself is not a place you want to spend time. It is a frozen, lightless realm where temperatures hover within a few degrees of absolute zero, the lowest temperature physically possible, 273 degrees below the Celsius scale. The sun, from that distance, has shrunk to nothing more than the brightest star in a sky of strangers. No warmth, no day, no reference point for anything familiar, and then you push past it. You cross the heliopause, the boundary where the sun's solar wind finally loses the battle against the pressure of interstellar space. This is the edge of what scientists call the heliosphere, the magnetic bubble our sun creates around itself. NASA's Interstellar Boundary Explorer mission has spent years mapping this boundary, and what lies beyond it is something our instruments have only recently begun to measure directly. Beyond the heliopause, the full force of galactic space hits you unfiltered, and what's out there is not nothing. The interstellar medium, the material filling the space between stars, is mostly hydrogen at an average density of about 1 atom per cubic centimeter. To put that in perspective, the best vacuum we can create in a laboratory on Earth still contains millions of particles per cubic centimeter. Interstellar space is far emptier than anything we can manufacture. And yet, and this is crucial, it is not empty enough to be harmless at the right speeds. Physicists working on the Breakthrough Starshot initiative studied this problem in detail. Breakthrough Starshot was a real, funded project announced in 2016 by investor Yuri Milner, with Stephen Hawking among its most prominent supporters. The goal was to develop laser-propelled nanosails, tiny, gram-scale probes capable of crossing to the Alpha Centauri system in 20 to 30 years by traveling between 15 and 20% of light's velocity. That translates to roughly 60,000 kilometers per second. At that kind of velocity, a hydrogen atom floating in interstellar space is no longer benign. Jonathan McDowell, an astrophysicist at the Harvard-Smithsonian Center for Astrophysics, put it plainly: at those speeds, a hydrogen atom is a cosmic ray. It hits with the energy of a particle in an accelerator. Thousands of these collisions happen every second against the forward surface of anything moving through the interstellar medium that fast. And then there's the dust. Interstellar dust grains, tiny particles of silicate, carbon and metals, are scattered throughout the space between stars at densities of a few hundred to a few thousand grains per cubic kilometer. That still sounds negligible, but researchers calculated that over a 4-light-year journey at significant velocity, a surface of just 1 square centimeter would absorb roughly 10 million collisions from particles at the smallest detectable scale, and potentially several dozen impacts from larger grains capable of blasting craters, causing localized melting and penetrating centimeters deep into a solid shield. Their estimate for surface erosion from interstellar dust alone, about 1.5 millimeters stripped from the front of a craft the size of a postage stamp. For anything larger and slower, anything carrying life support, anything carrying a human, the engineering challenge compounds into something that borders on philosophical impossibility. Now layer cosmic rays on top of all that. These are high-energy particles, mostly protons, accelerated to extraordinary energies by the shock waves of supernovae across the galaxy. Inside the heliosphere, the Sun's magnetic environment deflects a meaningful fraction of these particles, offering a degree of protection we rarely think about. Once you're outside it, that protection is gone. The full galactic cosmic ray flux passes through you unimpeded. For a biological system, for a person, the cumulative radiation exposure over decades of interstellar travel without shielding would be catastrophic. We already see measurable cognitive effects in astronauts from the comparatively mild radiation environment of low Earth orbit. What interstellar space would do to the human body over years or decades is something we don't fully understand yet, and the early data is not reassuring. So you are traveling through a field of charged particles, microscopic shrapnel, and ionizing radiation. Everything in your path is trying to erode, irradiate, or destroy anything you've brought with you. This is the journey, the crossing, before you've even come within sight of your destination, but you keep going. Years pass, perhaps decades. The sun behind you fades to just another bright point among thousands. Ahead, faintly red, barely luminous, Proxima Centauri grows slowly brighter. It shines at roughly 1/500th of the sun's visible light output. It is dim, it is small, about 1/7 the sun's diameter, and only about 12% of the sun's mass. To the naked eye, from a distance, it looks almost gentle. It is not gentle as you draw within a few billion kilometers, a distance that, on the scale of what you've already traveled, is almost trivially small. You start to feel the star, not as warmth, not as a glow, as a storm, because Proxima Centauri is fully convective, which means its entire interior churns from core to surface like a pot of boiling water that never stops. In our Sun, stable outer layers moderate the release of energy. Proxima Centauri has no such moderation. Its magnetic field lines tangle, compress, and snap on no predictable schedule, releasing enormous bursts of energy, flares, with terrifying frequency. The 2025 ALMA research by Kiana Burton and Meredith McGregor revealed something that changes the picture dramatically. Proxima Centauri's flaring activity at millimeter wavelengths follows a completely different and far more energetic pattern than what optical observations had led scientists to expect. In other words, previous studies of this star had been looking at only part of the data. The full picture, captured by ALMA, the only millimeter interferometer powerful enough to make these measurements, shows a star that is significantly more violent than we realized, more frequent bursts, more energy released, a greater threat to anything nearby, and the March 2016 superflare puts an exclamation point on all of it. That single event released energy roughly 10 times greater than any previously detected Proxima flare. For any planet sitting as close as Proxima b, which orbits at just 5% of the Earth-Sun distance, The incoming radiation from that superflare would have arrived 4,000 times more intensely than the worst solar flares that strike Earth. Modeling from the research team shows that repeated bombardment at that rate is sufficient to strip 90% of the ozone from an Earth-like atmosphere within 5 years. Total depletion within a few 100,000 years, which, on geological timescales, is barely a breath, and the ultraviolet radiation from that single event. It would have hit the surface of Proxima b at roughly 100 times the dose needed to kill the hardiest UV-resistant microorganisms we know of, 100 times the lethal threshold, from one flare. On a planet that has endured billions of years of this, we have not yet talked about tidal locking, about what happens to a world when it stops rotating entirely, one face permanently scorched and the other in permanent frozen dark. We have not talked about what the complete loss of a magnetic field does to a planet's chances of holding onto its atmosphere, and we haven't touched on the discovery announced in August of 2025, something the James Webb Space Telescope found in this very system that nobody expected, something that may change everything we thought we understood about Proxima Centauri's cosmic neighborhood, because Proxima Centauri is not alone. It belongs to a triple star system, Alpha Centauri A, Alpha Centauri B, and Proxima itself, and one of those companions has just revealed a secret that raises enormous questions. What did Webb find, and why does it matter so deeply for the story of this journey? One of the questions I get most often from people who watch these videos is, how do I actually connect with any of this? And I understand that feeling completely. You hear about stars 4 light years away, planets orbiting in the dark, and it can feel abstract. The thing is, some of what we're talking about tonight, you can actually see with your own eyes, through your own telescope. I've been using the Celestron StarSense Explorer for a while now, and what strikes me most about it is how quietly it removes every barrier that used to keep people from starting. It uses your phone's camera to map the sky above you in real time, then guides you to whatever you want to find. No experience needed, no charts to memorize. The first time you find a nebula on your own, something shifts. If you've been thinking about getting a telescope, the link is in the description and pinned on the comments. Now let's go back to where we were. You have arrived. After years of travel through the frozen dark, through a gauntlet of charged particles and radiation that no material we currently know how to build could fully withstand, you are here, in orbit, or something close to it, around Proxima Centauri, and the first thing you notice is the light. It's wrong. Our sun bathes our world in white-yellow warmth. Proxima Centauri, being a red dwarf, emits the vast majority of its energy as infrared radiation, heat rather than visible light. The glow it casts is a deep, dull crimson. Imagine a sky permanently lit like the last embers of a dying campfire. The star hangs in the sky, visually larger than our sun appears from Earth because Proxima b orbits so much closer, but it feels dim, muted, more like a warm coal than a burning lamp, and it never moves. This is one of the most profound and disorienting realities of Proxima b's existence. The planet is almost certainly tidally locked. This means that one face of the world always points toward its star, and the other face always points away into permanent night. The same way our moon always shows us the same side, never rotating relative to us. Proxima b has, over billions of years, been slowed to a rotational standstill by the gravitational pull of its star. It no longer has a day, it no longer has a night in the way we mean those words. It has 2 permanent hemispheres, one that has never seen darkness, one that has never seen light. The physics of tidal locking aren't mysterious. They're the straightforward result of gravitational forces acting over geological timescales. A body orbiting close enough to a massive object will experience stronger gravitational pull on the near side than the far side. This difference in force, the tidal force, acts like a brake on the planet's spin, gradually slowing it until the rotation synchronizes with the orbit. For rocky planets orbiting in the habitable zones of red dwarf stars, which are much dimmer and therefore require much closer orbital distances than Sun-like stars, this process happens relatively quickly in astronomical terms. Proxima Centauri is 4.5 billion years old. Proxima b has had more than enough time to lock completely. What does a tidally locked world actually look like? The day side, the hemisphere permanently facing the star, is likely a region of intense, sustained heat. Computer models of tidally locked rocky worlds suggest that equatorial temperatures on the day side could reach several hundred degrees Celsius in the absence of any atmosphere to redistribute heat. The night side, permanently shielded from the star, would plunge to temperatures far below the freezing point of carbon dioxide, cold enough to freeze gases out of the air entirely. Between these two extremes lies what scientists call the terminator, a ring-shaped boundary circling the entire planet where the star is always sitting on the horizon. This is the only place on Proxima b where the sun neither rises nor sets, but simply hovers perpetually at the edge of the world, where dawn never ends and dusk never begins. If Proxima b has any liquid water, any breathable air, any zone remotely hospitable to something like life, theoretical models suggest it would be here, on that narrow, endless ring of eternal twilight. But here is where the story fractures in multiple directions at once, because whether Proxima b has an atmosphere at all is one of the most contested and deeply uncertain questions in modern astrophysics. For an atmosphere to persist on a planet, it needs to be replenished faster than it is stripped away. And what strips planetary atmospheres? Exactly what Proxima Centauri produces in overwhelming abundance: ultraviolet radiation, X-rays, and energetic particles from stellar flares. Every flare event, and we established that there are nearly 10 per hour, blasts the planet with radiation. Without a strong magnetic field to deflect these particles, the upper atmosphere is continuously bombarded. Molecules are ionized. Ions are accelerated away from the planet by the stellar wind. The atmosphere bleeds into space. Whether Proxima b has such a magnetic field is unknown. We cannot directly measure it from Earth, but we can reason about it. A planet's magnetic field is generated by motion in its liquid, metallic core, a process driven partly by the planet's rotation. A tidally locked world, rotating extremely slowly relative to its orbital period, may have a weaker dynamo effect than a faster rotating world like Earth. Some models suggest Proxima b could still generate a meaningful field despite its slow rotation. Others suggest the field would be too weak to offer meaningful protection against the stellar environment. The truth is, we don't know yet. What we do know is that Mars, a planet with a much weaker magnetic field than Earth, has been slowly stripped of its atmosphere over billions of years by the relatively mild solar wind from our own comparatively quiet sun. Now imagine that same process accelerated by a star 10 times more active at a fraction of the orbital distance. The math is difficult to escape, and yet, life has a way of finding gaps in logic. In the search for life on Proxima b, researchers have modeled scenarios where thick carbon dioxide atmospheres survive despite flaring, where the replenishment rate from volcanic activity outpaces the loss rate from irradiation. They have modeled oceans kept liquid by the greenhouse effect of a dense atmosphere, even on the terminator ring. They have even modeled underground ecosystems, organisms living in liquid water beneath a frozen surface, shielded from radiation by kilometers of rock, not unlike the environments we now suspect may exist on the icy moons of Jupiter and Saturn in our own solar system. None of these scenarios have been ruled out. None have been confirmed. What makes Proxima b such a compelling obsession for scientists is precisely this ambiguity. It sits close enough to its star to receive warmth. It sits in what we call the habitable zone, the range of distances where liquid water could theoretically exist on a surface, and it is, by an enormous margin, the closest potentially habitable planet we know of outside our solar system. But habitable zone is a term that was coined with our Sun in mind. It describes orbital distance. It says almost nothing about whether a planet can hold on to water, maintain a stable climate, or protect organic chemistry from radiation. Around a red dwarf like Proxima Centauri, the habitable zone sits so close to the star that all the rules change, and that's what makes this entire story so genuinely uncertain and so fascinating. Which brings us to something that happened in August of 2025, something that no one fully predicted, something that shifted the entire conversation about this stellar neighborhood. Astronomers working with the James Webb Space Telescope, the most powerful space observatory ever built and launched, announced compelling evidence of a giant planet orbiting Alpha Centauri A, not Proxima Centauri, but its companion star in the triple system. Alpha Centauri A is a Sun-like star, similar in mass and age to our own Sun, sitting just 4¼ light-years away. And Webb's mid-infrared instrument, known as MIRI, detected something orbiting it, something over 10,000 times fainter than the star itself, separated from it by roughly twice the Earth-Sun distance. If the detection is confirmed, this candidate planet would be approximately the mass of Saturn, sitting at the very edge of Alpha Centauri A's habitable zone. It would be the closest planet to Earth ever found orbiting within the habitable zone of a Sun-like star. As a gas giant, it wouldn't support life on its own surface. But a gas giant in that region implies something else, something the researchers were careful to note. Where giant planets orbit, smaller rocky worlds often follow, and a rocky planet in the habitable zone of a Sun-like star in the nearest stellar system to Earth, that would rewrite everything. Now, the detection is not without complication. The team observed Alpha Centauri A in August of 2024 and found the candidate object. They returned in February and April of 2025 and found nothing. The planet had, in Caltech PhD student Aniket Sanghi's words, disappeared. But simulation of millions of possible orbits showed that in roughly half of the stable trajectories, the planet would have moved too close to the star to be visible during those follow-up windows. The disappearance isn't proof of absence. It may simply be the planet completing an arc that momentarily brought it behind the glare. Co-author Charles Beitman of NASA's Jet Propulsion Laboratory described it directly. If confirmed, this would become a touchstone object for exoplanet science. NASA's Nancy Grace Roman Space Telescope, planned for launch no later than May 2027, is already being positioned to take the next look. So here is what the picture actually looks like from where we're standing now. You have traveled across 4.24 light-years of interstellar space. You have survived the Oort Cloud, the heliospheric boundary, the cosmic ray flux, and the dust. You have arrived at a dim red star that erupts 10 times an hour. You are orbiting a world that may or may not have an atmosphere, may or may not have liquid water, and sits on the inner edge of what we optimistically call a habitable zone, while being blasted continuously by stellar radiation. And just 4 light-years in the opposite direction, the companions of that red star may harbor their own planetary system, one that includes a world with the mass of Saturn sitting at the right distance from a star, far more like our Sun. The Alpha Centauri system isn't just a destination, it is an entire neighborhood, and we are only now, just barely, beginning to see what's inside it. But the question that most researchers wrestle with in quiet moments isn't whether there are planets here. The question is whether any of them could have kept the ingredients for life from being destroyed. And that question leads into territory far stranger than orbital mechanics or atmospheric chemistry. It leads into the deep question of what life actually requires, and how we'd even know if something were alive on a world we cannot visit, cannot sample, and can only observe as a faint signal from 40 trillion kilometers away, because the next part of this journey doesn't take us closer to the star. It takes us inward, into the physics of what makes a world alive, into what it would mean for chemistry to organize itself under Proxima Centauri's violent sky, into the molecules that might survive there, and into the one signal that, if we ever detected it, would change the history of our species forever. Let's say, for the sake of everything that follows, that Proxima b has held onto some kind of atmosphere. Let's say that volcanic activity has been replenishing gases faster than the stellar wind can strip them away. Let's say the Terminator ring, that eternal band of twilight, is just warm enough and just sheltered enough for liquid water to pool somewhere on the surface. Let's grant the planet every possible advantage. Even then, we face a question so deep it borders on philosophy. How would we ever know if something was alive there? This is not a trivial problem. It is arguably the central problem in astrobiology right now, and the more carefully you look at it, the stranger and more humbling it becomes. The tool scientists use to look for life across interstellar distances is the spectrum. When starlight passes through a planet's atmosphere, different molecules absorb different wavelengths of that light. By measuring which wavelengths are missing when the light reaches our telescopes, we can infer what gases are present. It's a remarkably elegant method. It's also riddled with ambiguity. For decades, the dream biosignature, the chemical fingerprint that scientists most hope to find in an alien atmosphere, was oxygen. The reasoning was straightforward. On Earth, the oxygen in our atmosphere is almost entirely produced by living things. Photosynthetic organisms, plants, algae, cyanobacteria, take in carbon dioxide and water, harness energy from sunlight, and release oxygen as a byproduct. Without constant biological replenishment, atmospheric oxygen reacts with rocks, minerals, and volcanic gases and disappears over geological timescales. So if you find oxygen in an atmosphere, logic suggests something living must be producing it, except the situation around a red dwarf star like Proxima Centauri is far more complicated than that. And this is where the science becomes genuinely unsettling. Research published in peer-reviewed journals and highlighted by NASA's astrobiology program has shown that planets orbiting red dwarfs may be able to accumulate significant amounts of oxygen in their atmospheres through purely non-biological processes. Here is how. When a red dwarf is young, and Proxima Centauri was once young, about 4.5 billion years ago, it is far more luminous than it becomes in its stable adult phase. That early period of intense radiation can drive an enormous amount of water photolysis. Ultraviolet light splits water molecules in the upper atmosphere into hydrogen and oxygen. Hydrogen, being the lightest element, escapes into space. Oxygen, being heavier, stays behind. Over millions of years, this process can build up what looks, from a distance, like a meaningful oxygen-rich atmosphere, with no life involved whatsoever. Researchers call this a false positive. You look at the spectrum, you see oxygen, you think life, and you might be completely wrong. This is not a theoretical edge case. Victoria Meadows at the University of Washington and her colleagues at NASA's Virtual Planetary Laboratory team have written extensively about this exact scenario, emphasizing that oxygen detection around M-dwarf planets, red dwarf planets, is particularly prone to abiotic false positives precisely because of the extreme early radiation environment those stars produce. Their work, published in the journal Astrobiology, made clear that oxygen alone, even abundant oxygen, cannot be treated as a reliable biosignature around a star like Proxima Centauri without additional context. So what do scientists actually look for when they're being rigorous about it? The answer, it turns out, is not a single gas. It's a combination, a pattern of chemical disequilibrium that would be very difficult to explain without some active biological process maintaining it. The most promising combination, according to research highlighted by NASA's astrobiology program, is the simultaneous presence of methane and carbon dioxide without a corresponding abundance of carbon monoxide. Here's why that matters. Methane and carbon dioxide react with each other chemically. Left alone, they destroy each other over time. If you find both in an atmosphere at significant levels, something must be continuously producing at least one of them to keep both present at the same time. On Earth, the primary source of atmospheric methane is biological, microbial life that metabolizes organic matter in low oxygen environments. Methane breaks down quickly under ultraviolet radiation, which means its persistent presence implies continuous replenishment. Now add the carbon monoxide clue. Many non-biological processes that produce methane also produce carbon monoxide as a byproduct, but surface microbial life, if present, tends to consume carbon monoxide. It's an easily accessible energy source for certain metabolisms. So the signal researchers are looking for isn't just methane and carbon dioxide together, it's methane and carbon dioxide together without the carbon monoxide you'd expect from abiotic sources. That absence is itself a kind of fingerprint. And then there's nitrous oxide, often overlooked in popular science writing. Nitrous oxide, produced on Earth almost entirely by microbial processes in soils and oceans, is actually considered one of the more reliable biosignature candidates, precisely because there are so few abiotic pathways to produce it in meaningful quantities. Unlike oxygen or methane, it doesn't have a well-established geological production mechanism. If you detected nitrous oxide in a planetary atmosphere at levels similar to Earth's, the non-biological explanations would be extremely limited. None of these gases have been detected on Proxima b. To be precise about the current state of knowledge, as of now, we have not been able to directly characterize Proxima b's atmosphere at all. The planet does not transit its star from Earth's vantage point. It doesn't pass in front of Proxima Centauri in a way that allows us to use the transit spectroscopy method, where starlight filtered through the atmosphere reveals its composition. Direct imaging of a planet this small and this close to its dim, flare-active parent star is beyond the current limits of our instruments. The James Webb Space Telescope has focused its extraordinary infrared vision on the Alpha Centauri system, delivering the planet candidate discovery around Alpha Centauri A. But Proxima b itself remains, chemically, a blank page. That blank page is not emptiness, it is possibility, and the possibilities, when you sit with them, become increasingly strange. Consider what life on Proxima b might actually look like, if it exists at all. The environment is so radically different from anything life evolved in on Earth that any organisms present would almost certainly reflect those differences in profound ways. Life on Earth began in an environment with relatively stable sunlight, a robust magnetic field, and a steady planetary rotation that created day-night cycles, driving biological rhythms across billions of years. Proxima b, if tidally locked, has none of that. Its day side is permanent, its night side is permanent. The only variable environment is that terminator ring, the strip of eternal twilight where conditions might be marginally tolerable. What kind of biology survives under a crimson sky that never changes? What kind of organism adapts to radiation bombardment so intense that the most UV-resistant microorganisms we know of on Earth would die from a single superflare? What chemistry organizes itself under those conditions? We genuinely don't know. And this is one of the most important things to hold on to as you think about the search for life beyond Earth. Our entire framework for what life looks like, what it needs, and what chemical signals it produces is built on a sample size of one planet, one biosphere, one evolutionary history. Every assumption we make about biosignatures, about habitability, about the minimum conditions required for chemistry to organize itself into something self-replicating. All of it is grounded in terrestrial life, which is the only life we have ever studied. This creates a profound problem. Life on Proxima b, if it exists, may have followed a completely different evolutionary path. It may produce gases we're not looking for. It may consume gases we'd expect to find. It may organize itself in ways that leave no atmospheric fingerprint we currently know how to read. It might be so different from what we call life that we could observe its planet for decades and never recognize it. Astrobiologists call this the problem of the shadow biosphere, the idea that life could in principle exist in forms so biochemically alien that our instruments, calibrated to Earth life, would simply miss it. On Earth, we even discuss the theoretical possibility that a separate lineage of life, using different chemistry, different solvents, different molecular building blocks, could have arisen independently and still exist here, undetected, because we've never looked for it in the right way. If that seems far-fetched, consider that the vast majority of microbial life on Earth went completely unknown to science until molecular sequencing techniques revealed its existence in the 1980s and 90s. We shared a planet with it for the entirety of human history and had no idea it was there. Now put that on a world 4.24 light-years away, orbiting a violent red star, under conditions unlike anything in our direct experience. Here is what that means practically. Even if we build a telescope powerful enough to characterize Proxima b's atmosphere, and there are serious proposals for doing exactly that, including designs for telescopes capable of directly imaging Earth-sized planets around nearby stars, a negative result would not prove the absence of life. It would only prove the absence of the specific biosignatures we thought to look for, and a positive result, finding methane, carbon dioxide, nitrous oxide in the right combinations, would still not be proof. It would be a compelling suggestion, a reason for extraordinary excitement, a reason to look harder. The search for life on Proxima b is not a problem with a clean answer waiting at the end. It is an exercise in building confidence, slowly and painstakingly, in a universe that keeps its secrets carefully. And yet, there's something else that scientists have begun to consider, something that takes the question of life around Proxima Centauri and turns it in a direction most people haven't thought about. What if the relevant question isn't whether life exists on Proxima b, the closest planet in the habitable zone? What if the relevant question is whether life could have migrated through space between the Alpha Centauri system and our own? What if the same mechanism that seeded life across different planets within a single solar system, rocks blasted off one world by asteroid impacts, carrying microbial stowaways across the void, could operate across the gap between stars, Panspermia, the idea that life, once it exists somewhere, can travel, and at 4.24 light-years, Proxima Centauri is the nearest possible destination or source. The numbers on this are worth understanding carefully. The distances are staggering, but they are not infinite, and some of the research into how microorganisms survive in the harsh conditions of space, exposure to vacuum, radiation, temperature extremes, suggests that certain organisms can endure for extraordinary lengths of time when encased in rock. What might have traveled between our Sun and Proxima Centauri over 4.5 billion years? That question doesn't have an answer yet, but scientists have begun to think seriously about how to look for it, and that line of thinking leads directly into the next territory this journey takes us, into what we now understand about the actual history of life on Earth, what it took for that chemistry to organize itself in the first place, and why the conditions on Proxima b are at once so alien and so hauntingly familiar. Because there's a period in Earth's own deep past, a time before complex life, before oxygen, before almost everything we recognize as living when our world looked, in some ways, remarkably similar to what Proxima b might look like today. What can that tell us about what might be waiting there? That's exactly where we're going next. If you are enjoying this journey, make sure to give this video a like and subscribe. You will be part of a community that explores the cosmos together. 4.5 billion years ago, Earth was not the world you know. There were no forests, no oceans teeming with fish, no birdsong, no soil, no oxygen in the air. There was, in fact, almost nothing we would recognize as hospitable. And yet, somewhere in that hostile, scalding, radiation-drenched chaos, something happened. Something so improbable, so chemically intricate, and so consequential that it changed the entire trajectory of this planet forever. Life began. And the reason this matters, the reason it belongs in a story about Proxima Centauri, is that the early Earth was, in certain key ways, not entirely unlike what Proxima b might look like today. Studying how life started here under those original brutal conditions is one of the most direct tools scientists have for reasoning about whether life could start there. So let's go back, all the way back. The Earth formed approximately 4.54 billion years ago from the same cloud of gas and dust that gave birth to our Sun. In its earliest phase, a period geologists call the Hadean Eon, named after the Greek underworld, because the name is accurate. The surface was largely molten. Asteroid and comet impacts were so frequent that any crust that tried to solidify was repeatedly shattered and remelted. The Moon, newly formed from a catastrophic collision between proto-Earth and a Mars-sized object, sat far closer than it does today, raising tides that dwarfed anything in the modern ocean. Volcanic activity was near continuous. The atmosphere was thick with carbon dioxide, nitrogen, water vapor, and traces of methane and ammonia, a deeply toxic mix by any modern standard. And the Sun, despite being the same star, was younger then. Paradoxically, a younger sun is a dimmer sun. In its early phase, our star put out only about 70% of the energy it produces today. Earth should, by the simple math of solar radiation and orbital distance, have been frozen solid during the Hadean and early Archean periods. This is known as the faint young sun paradox, and it has been a subject of serious scientific debate for decades. The leading resolution is that the early Earth's atmosphere was so rich in greenhouse gases, especially carbon dioxide and methane, that it trapped enough heat to keep liquid water stable despite the reduced solar output. Now hold that thought. A dim star, a thick greenhouse atmosphere, liquid water present despite conditions that should, on paper, preclude it. Does that sound familiar? Because that is almost exactly the scenario that some researchers model as a possible survival pathway for Proxima b, a thick carbon dioxide atmosphere trapping enough of the star's infrared output to maintain liquid water on the terminator ring, despite the star's dimness and the planet's challenging radiation environment. The parallel isn't perfect, it never is, but it is striking enough that astrobiologists take it seriously as a reference point. Now, when did life actually appear on Earth? This is where the science becomes both more precise and more staggering. The oldest confirmed evidence of life on Earth comes from microfossils and carbon isotope signatures found in rocks from Western Australia and Canada. Some of these biosignatures dating back approximately 3.7 to 3.8 billion years. There is more contested evidence, including carbon isotope ratios in 4.1 billion-year-old zircon crystals from Western Australia's Jack Hills Formation, suggesting that biological processes may have been occurring even earlier, potentially within just a few 100 million years of Earth's formation, while impacts were still frequent and the surface was still largely hostile. Think about what that means. Life didn't wait for Earth to become comfortable. It didn't bide its time until conditions were ideal. It seems to have erupted, almost impatiently, into whatever thin margin of habitability existed, as soon as liquid water became even intermittently stable. That urgency, if it reflects a genuine universal tendency of chemistry under the right conditions, has enormous implications. It suggests that life doesn't require paradise. It requires a threshold, a minimum set of conditions, and once those conditions are crossed, chemistry begins moving in the direction of self-organization with what looks almost like inevitability. What are those minimum conditions? Based on everything we've learned from the study of early Earth and from extremophile biology, the study of organisms that survive in conditions previously thought incompatible with life, the list is shorter than most people expect. You need liquid water, not an ocean, not even a lake. A film of liquid water, intermittent on the surface of a mineral grain, is enough to enable the chemistry of life. Water is the universal solvent in which organic reactions occur, the medium through which molecules find each other, the environment in which concentration gradients can build up and drive thermodynamic processes. You need a source of energy. On early Earth, that energy came from multiple sources simultaneously. Volcanic heat at hydrothermal vents, chemical gradients between different types of rock and fluid, ultraviolet radiation driving reactions in shallow surface pools. Life, as we've learned, is extraordinarily flexible about where it gets its energy. Organisms on Earth have been found metabolizing sulfur compounds in volcanic springs, harvesting energy from radioactive decay in deep mine water, living on the chemical energy of hydrogen gas, seeping from rock-water reactions in the absence of any sunlight whatsoever. You need organic chemistry, carbon-based molecules capable of forming the complex structures that eventually become self-replicating. We now know that organic molecules are not rare in the universe. They are extraordinarily common. Amino acids have been found in meteorites. Complex carbon chemistry has been detected in interstellar gas clouds light years across. The raw ingredients are not the limiting factor, and you need time, or perhaps, and this is the part that upends conventional thinking, you need less time than we assumed. The Miller-Urey experiment of 1952 was the first modern demonstration that organic molecules could arise spontaneously from inorganic chemistry under conditions resembling early Earth. Stanley Miller and Harold Urey simulated a primitive atmosphere of water, methane, ammonia, and hydrogen, ran electrical sparks through it to simulate lightning, and within days produced amino acids, the building blocks of proteins. The experiment was revolutionary. It showed that the gap between chemistry and biology was not insurmountable, that the universe, under the right conditions, moves naturally toward complexity. Since then, the science has grown dramatically more sophisticated. Researchers studying hydrothermal vents, cracks in the ocean floor where superheated, chemically rich water pours into the cold deep sea, have proposed that these environments could have served as the original cradles of life. The work of researchers including Michael Russell and William Martin has developed detailed models of how the chemical gradients at alkaline hydrothermal vents could have driven the first metabolic reactions, the first instances of chemistry extracting energy from its environment in a structured, self-sustaining way. This isn't speculation. The chemistry has been demonstrated in laboratory conditions. The thermodynamics work, and critically, hydrothermal systems don't require sunlight. They don't require a stable surface. They don't even require the kind of benign surface environment we usually imagine when we picture a habitable planet, which means they could, in principle, operate on Proxima b. Even under that crimson, flare-scorched sky, even without a thick protective atmosphere, even if the surface of the planet is a radiation-blasted wasteland, because kilometers of rock are extraordinarily effective radiation shielding, a hydrothermal system buried beneath Proxima b's crust, driven by the tidal heating from the planet's gravitational interaction with its star, could in theory maintain liquid water and chemical gradients indefinitely, completely independent of what happens on the surface above. This is not the scenario most people picture when they imagine life on another planet. We tend to imagine surface life, green things, blue oceans, a sky, but the history of life on Earth increasingly suggests that life began in the dark, in the deep, in hot, chemically chaotic environments far from sunlight. The photosynthesis we take for granted, the ability of life to harvest energy directly from a star, is a later innovation, an extraordinary evolutionary development that happened hundreds of millions of years after life was already well established. The first life on Earth almost certainly never saw the sun. Hold that thought as you think about Proxima b, because if the first life on Earth didn't need sunlight, didn't need a stable surface, didn't need calm conditions, then the relevant question about Proxima b isn't whether its surface is habitable, it's whether anything anywhere inside or beneath that world crosses the threshold. And then there is the idea that has been quietly gaining traction in serious scientific circles for decades, not as a fringe hypothesis, but as a genuine mechanism worth investigating with mathematical rigor: Panspermia, the transfer of life between worlds carried inside rocks across the void. Within our own solar system, the evidence for this kind of material transfer is solid. Every substantial impact on a rocky planet launches material into space. Some of that material eventually falls onto other worlds. We have found meteorites on Earth that originated from Mars, identified by the unique chemistry of gases trapped inside them, matching the composition of the Martian atmosphere as measured by our landers. Rocks have traveled between Mars and Earth. The journey takes thousands to millions of years, but rocks are extraordinarily good at protecting their contents from the vacuum and radiation of space. Certain bacterial spores encased inside rock have been shown in laboratory experiments to survive conditions mimicking interstellar space for extended periods. Within our solar system, Panspermia is plausible enough that scientists take it seriously as a potential explanation for how life on Earth could be related to any life that ever existed on early Mars. The reverse is equally possible, that Earth, bombarded by impactors in its early history, could have sent biology-laden rocks toward Mars, now extend the question across the gap between stars. This is where it gets genuinely speculative, but grounded in real physics. The distances are far larger. The travel times, for rocks launched at typical impact velocities, are measured not in millions of years, but in hundreds of millions or billions. Whether microbial life could survive in dormancy for that long, even inside rock, even shielded from most radiation, is unknown. Some theoretical analyses suggest it is not impossible, particularly if the organisms are deeply embedded in rock and exposed primarily to cosmic rays rather than ultraviolet light. Others suggest the radiation dose over such timescales would be lethal for any known biological molecule, but here's what makes this more than just speculation. The Sun and the Alpha Centauri system, including Proxima Centauri, were not always 4.24 light-years apart. Stars move relative to each other over galactic timescales. There may have been periods in the deep past when the two systems were somewhat closer. The exchange of material, while still extraordinarily improbable in any single event, becomes slightly less impossible when considered over billions of years and enormous numbers of impact events. And if life arose here and traveled there, or arose there and traveled here, then the life we might find on Proxima b would not be alien in any meaningful biochemical sense. It would be related to us. It would share the same molecular architecture, the same genetic code perhaps, the same chirality of amino acids. It would be, in the most literal sense, family. That thought that the nearest potentially habitable world might harbor our distant biological cousins sits somewhere between beautiful and deeply disorienting. and it raises a question that no one has answered, that perhaps no one can answer with the tools we currently have. Is the universe full of life that all shares a common origin, seeded across space by the same ancient impacts that shaped the early solar system? Or is life rare enough that even the nearest star system has never felt the touch of biology at all? Neither answer, when you sit with it, is entirely comfortable. What we can say with confidence is this: the early Earth argument cuts both ways. It tells us that life can begin in hostile conditions faster and more stubbornly than we once believed. And it tells us that even 4.5 billion years of evolution, even all the complexity of the biosphere we now inhabit, began with something almost unimaginably simple: a membrane, a gradient, a molecule that could copy itself on Proxima b if any of the thresholds we've described are crossed. Liquid water, chemical energy, organic molecules, time. Then that same first step is at least conceivable, not guaranteed, not even likely by any rigorous probability estimate we can currently make, but conceivable. And in a universe this vast and this old, conceivable is a far larger category than we are intuitively built to appreciate. The journey doesn't stop here, because even if we accept, for the sake of imagining, that Proxima b has life, even microbial, even buried deep beneath radiation-blasted rock, the next question becomes the one that haunts every serious astrobiologist who has ever looked at that faint red star through a telescope at night. Could anything more complex have evolved there? Could 4.5 billion years of chemistry under Proxima Centauri's violent flickering light have produced something that thinks, something that builds, something that perhaps has already looked in our direction and wondered about the pale blue world orbiting that quiet yellow star? Let's say life began on Proxima b. Let's grant it every advantage we discussed: a hydrothermal vent buried beneath kilometers of rock, liquid water, organic chemistry, a chemical gradient providing energy. Let's say that, 4.5 billion years ago, the same improbable spark that ignited biology on Earth also ignited it there. What happens next? On Earth, the answer is nothing dramatic, not for a very long time. This is one of the most sobering facts in the entire history of life on our planet, and it doesn't get nearly enough attention. Life appeared on Earth, as far as we can tell, within the first few 100 million years. Simple, single-celled microbial life, bacteria, archaea, organisms without a nucleus, without complex internal machinery, without any of the elaborate cellular structures that more complex life depends on. And then, for approximately 2 billion years, almost nothing changed. 2 billion years. That is longer than the current age of the solar system will be from now. For 2 billion years, life on Earth remained microbial. It filled the oceans, it colonized volcanic rocks. It developed extraordinary metabolic diversity, learning to harvest energy from sunlight, from sulfur, from iron, from hydrogen. But it did not become complex. It did not develop cells with nuclei. It did not develop multicellularity. It did not develop anything resembling an animal, a plant, or a fungus. The jump from simple prokaryotic life, bacteria and their cousins, to complex eukaryotic life, with its membrane-bound nucleus and elaborate internal organelles, happened only once in the entire history of Earth. Once. And it appears to have required a specific event, one bacterial cell being engulfed by another, and rather than being digested, surviving inside its host and eventually becoming a permanent resident. That resident became the mitochondrion, the energy-generating structure inside almost every complex cell on Earth today. This event, called endosymbiosis, is described in detail in the work of the biologist Lynn Margulis, whose theory was initially dismissed and eventually vindicated by molecular evidence. The mitochondrion has its own DNA, separate from the nucleus. Its genetic code is distinct from that of the rest of the cell. It replicates independently. It is, unmistakably, a former free-living bacterium that was absorbed into a larger cell roughly 1.5 to 2 billion years ago, and never left. That single, unlikely merger gave complex life its engine. Without it, there are no animals, no plants, no fungi, no brains, no eyes, no civilization. And as far as we can tell, it happened once, in the entire history of life on Earth. Once this matters enormously for Proxima b, because if the jump from simple to complex life required a specific, extraordinarily improbable event, an event that on Earth took 2 billion years to happen by chance, even after life was already well established, then complex life may be vanishingly rare even on planets that host microbial biology. The universe could be teeming with bacteria and yet nearly empty of anything more elaborate. This is one version of what the cosmologist and physicist Stephen Webb and others thinking about the Fermi paradox have called the Great Filter. The idea is elegant and deeply troubling. The universe is old, it is vast, it is full of stars with planets, the ingredients for life are widespread, and yet we see no evidence anywhere of another technological civilization, no signals, no megastructures, no unambiguous signs of intelligence beyond Earth. The silence is deafening. The Great Filter is the name given to whatever explains that silence. Whatever step in the development from chemistry to cosmic civilization is so difficult, so improbable, that almost no planet ever crosses it. And the critical question, the one with the most profound implications for humanity's future, is this: is the Great Filter behind us or ahead of us? If the Great Filter is behind us, if it is something like the origin of life itself, or the invention of the eukaryotic cell, or the specific chain of events that led to multicellular animals, then we are the lucky survivors of an extraordinarily improbable gauntlet. We made it through. The silence around us is the silence of a universe where almost no one else did, and our future, while uncertain, is at least open. If the Great Filter is ahead of us, if the difficult step is something that technological civilizations tend to encounter after they arise, then the silence is a warning. Every civilization that reached our level of development eventually encountered something it could not survive, a self-inflicted catastrophe, a physical law that makes interstellar expansion impossible, something we haven't thought of yet. And the fact that we are here now, looking out at a quiet universe, means we are approaching that filter, not receding from it now. Bring Proxima Centauri into this framework, because the nearest star system to our own is one of the most important data points we have, or could have, for thinking about which version of the Great Filter story is true. If we were to study Proxima b and find nothing, no atmospheric biosignatures, no signs of biological activity, no chemical disequilibrium suggesting an active biosphere, that absence would be consistent with the Great Filter being at the origin of life step, or the simple to complex life step. It would suggest that even in the most favorable nearby environment, life simply doesn't always take hold. It would push the filter toward the early stages. That would be, paradoxically, reassuring, because it would mean the filter is behind us if we were to find simple microbial life on Proxima b. And this is the discovery that Carl Sagan and many who followed him most hoped for and most feared simultaneously. The implications would be staggering. It would mean life arises readily under the right conditions. It would mean the Great Filter is not at the origin of life step. It would push the filter somewhere later, and it would make the silence of the universe, the absence of any complex or intelligent civilizations detectable by our instruments, considerably more alarming. Because if life starts easily and intelligence still doesn't emerge or doesn't survive, then the filter must lie somewhere in between, and we don't know where. And if, an extraordinary if, one that currently has no evidential support but cannot be philosophically excluded, we were to find signs of complex life on Proxima b, signs of something more than microbial, signs of something that had evolved organs, nervous systems, behavior, then the Great Filter must lie even later in the chain, somewhere between complex life and technological civilization. Somewhere in the territory we are currently navigating ourselves. This is why the philosopher Nick Bostrom famously wrote in a widely cited paper that finding even simple life on Mars or anywhere nearby would be in some sense bad news for humanity, not because life is bad, but because its presence would constrain where the great filter must be and move it closer to us in time. That argument extends with even greater force to Proxima Centauri. But let's step back from the philosophical precipice for a moment and look at what the actual physical conditions of Proxima B's star tell us about the evolution of complexity, because they have something important and specific to say. For complex life to evolve on any world, time is not sufficient. You also need stability. You need an environment that remains within a survivable range for long enough that natural selection can accumulate the improbable innovations, the mitochondrion, the nucleus, the multicellular body plan, the nervous system, that turn a bacterium into something capable of experiencing the universe. Proxima Centauri presents a profound challenge on this front, not just because of its super flares, extraordinary as those are, but because of the nature of red dwarf stellar evolution as a whole. Red dwarfs are extraordinarily long-lived. Proxima Centauri will continue burning hydrogen on the main sequence for approximately 4 trillion years. Our Sun, by contrast, has about 5 billion years left before it begins its transition off the main sequence. On the scale of stellar lifetimes, red dwarfs are nearly immortal. This sounds like an advantage for the evolution of complex life. More time means more opportunities for evolutionary innovation, more chances for improbable events to occur, and in some abstract sense, that's true. But the early phase of a red dwarf's life, the first few billion years, is where the problem lies. Young red dwarfs are dramatically more active than old ones. They flare constantly. They pour out ultraviolet and X-ray radiation at rates that would sterilize the surface of any nearby planet. Proxima Centauri, at approximately 4.85 billion years old, has calmed down considerably from its youth. But it was not always this quiet in its early history. It was far more violent, and any planet in its habitable zone would have been subjected to that violence during precisely the period when life on Earth was making its most critical early transitions. Research published in the journal Astrobiology and elsewhere has modeled the cumulative radiation dose experienced by a planet in Proxima B's position over the lifetime of the star. The results are sobering. The integrated radiation exposure over the first 1 billion to 2 billion years of the planet's existence is, in the models, sufficient to create a serious barrier to the kind of stable surface-level chemistry that may be required for some early evolutionary transitions. This doesn't make complex life impossible. Biology is stubborn in ways that consistently exceed our expectations, but it does mean that the path from simple to complex life on Proxima b, if it was ever taken, would have faced obstacles that life on Earth, orbiting a more stable, less flare-active star, did not encounter to the same degree. And there is one more factor that seldom gets the attention it deserves in popular discussions of habitability: gravity, and its role in shaping the biological potential of a world. We don't know the mass of Proxima b with precision. What we know from the radial velocity measurements that detected it is its minimum mass, approximately 1.27 times the mass of Earth. The actual mass could be higher, depending on the inclination of its orbit relative to our line of sight. If Proxima b is significantly more massive than Earth, its surface gravity would be correspondingly stronger. Higher gravity changes everything about the evolution of life on a surface. It affects the maximum size of organisms, the energetics of movement, the structure of any possible ecosystem. It also affects the planet's interior. Higher mass planets retain heat longer, drive more volcanic activity, and maintain magnetic field generating convection in their cores for longer periods. Whether that is good or bad for habitability depends on the specific values involved, in ways that are genuinely uncertain. What we can say is that Proxima b is not Earth. It is not a slightly modified version of our planet, dropped into a slightly different orbit around a slightly different star. It is a genuinely alien world, shaped by forces that have no close parallel in our solar system, and any life that arose there would be the product of those forces in ways we can only begin to imagine. And yet, the imagining matters. It is not idle speculation, it is the engine of science. Every time humanity has tried to imagine what might exist beyond the edge of its knowledge, the attempt has eventually produced instruments, experiments, and ideas that transformed imagination into understanding. Right now, the Roman Space Telescope, scheduled to be operational in the coming years, will expand our ability to detect and characterize exoplanets in ways that complement the work of JWST. Ground-based projects like the extremely large telescope currently under construction in the Atacama Desert of Chile will eventually have the mirror size and adaptive optics capability to directly image nearby Earth-sized planets. There are serious, peer-reviewed proposals for space-based coronagraph missions, telescopes designed specifically to block the blinding light of nearby stars and image the faint reflected light of their planets, that would be capable of spectroscopically characterizing Proxima b. These instruments are not fantasies, they are engineering projects with budgets, timelines, and teams of people working on them. The question of what Proxima b's atmosphere contains, the question that would tell us with more clarity than anything else currently available whether that world is alive, is not permanently beyond our reach. It may be within reach within our lifetimes. And if it is, if a telescope on the ground in Chile or in orbit above our atmosphere delivers a spectrum of Proxima b's atmosphere, showing methane and carbon dioxide without carbon monoxide, or nitrous oxide at biological levels, or some chemical pattern that current science would describe as a compelling biosignature, that moment will be, without exaggeration, the most significant scientific discovery in the history of our species. Not a curiosity, not an interesting data point, the discovery that we are not alone, that the universe produces life not just once, in one extraordinary accident on a pale blue planet, in an unremarkable corner of one galaxy among hundreds of billions, but at least twice, at least, within 4.5 light-years of our own front door. And that discovery would immediately raise the question that we confronted directly: what do we do with that knowledge? What does it mean for the long-dreamed, long-debated possibility of actually going there, of sending not just telescopes and signals, but something physical across the void between stars, to see with our own instruments up close what is there? Because that conversation, the actual physics and engineering of interstellar travel, the real proposals that serious scientists and engineers have put forward for crossing the gap to Proxima Centauri, is where this journey gets both most thrilling and most humbling. The universe does not make it easy. It never does. You want to go to Proxima Centauri, not metaphorically, not in a simulation, not as a radio signal bounced off a distant antenna. You want to send something physical, matter, molecules, instruments, or perhaps one day, people, across the 4.24 light-years of interstellar space that separate our solar system from that faint red star. The moment you seriously entertain that idea, the universe hands you a list of problems so long, so layered, and so brutally physical that most people who encounter it for the first time quietly set the ambition aside. Not because it is impossible in any absolute sense, but because the gap between what the physics allows and what human civilization has ever built is so enormous that it reframes the entire concept of what difficult means. Let's start with the most fundamental constraint: distance. 4.24 light-years sounds like a number. It doesn't feel like one, not until you try to move through it. The fastest human-made object ever launched as of the time this script was written traveled at approximately 17 kilometers per second relative to the Sun. To reach Proxima Centauri at that speed would take approximately 73,000 years. Not generations, not centuries, 73,000 years. Modern human civilization in its entirety, every city ever built, every language ever spoken, every empire that rose and fell, fits inside a window of roughly 10,000 years. We would need 7 of those windows, stacked end to end, just to arrive. So chemical propulsion, the rockets that have taken us to the Moon, to Mars orbit, past the outer planets, is not a path to the stars, not even close. The physics of chemical combustion simply cannot release energy at a rate sufficient to accelerate a meaningful payload to the speeds required for interstellar travel within any time frame that connects meaningfully to human experience. This is not an engineering limitation that better materials or bigger budgets can solve. It is a thermodynamic one. The energy stored in chemical bonds is simply not sufficient. To travel to Proxima Centauri in, say, 1,000 years, already a staggeringly long time frame by human standards, you need a spacecraft traveling at roughly 1/400th of the speed of light. That is approximately 750 kilometers per second. To reach that speed using the most energetic chemical reaction available, you would need a fuel-to-payload ratio so extreme that the mathematics become physically absurd. The rocket would need to be almost entirely fuel. The mass of propellant required to accelerate even a small payload to that velocity, using chemical means, would exceed the mass of everything humanity has ever built by many orders of magnitude. So what does serious science actually propose? The most discussed serious proposal for an interstellar mission in the current era is called Breakthrough Starshot. Announced in 2016, funded initially by the technology investor Yuri Milner, and developed in collaboration with a scientific advisory board that included some of the most respected names in astrophysics, Breakthrough Starshot proposed something genuinely radical. Forget conventional rockets entirely. Instead, use light itself as the propellant. The concept is elegant in its physics. A ground-based array of high-powered lasers on the scale of 100 gigawatts of combined output, roughly equivalent to the total electrical generating capacity of a large nation, would be focused onto an extraordinarily thin reflective sail attached to a gram-scale spacecraft. The pressure of the laser light on the sail would accelerate the spacecraft to approximately 20% of the speed of light. At that velocity, the journey to Proxima Centauri would take roughly 20 to 25 years. The spacecraft would arrive. It would fly through the system. It cannot stop. There is no mechanism for deceleration at the destination. And during that brief flyby, lasting hours or perhaps days, its instruments would gather data and transmit it back to Earth. The transmission would take 4.24 years to arrive, but arrive it would. Within roughly a quarter of a century after launch, and a few years after arrival, we would have data from another star system, direct data, measurements taken in situ at Proxima Centauri by instruments that were physically there. This is not science fiction. The physics of laser sailing is real. The concept of light pressure is textbook physics, experimentally confirmed. The question is purely engineering, and the engineering's challenges are extraordinary, though not clearly impossible. A laser array of 100 gigawatts does not currently exist. Building it would be one of the largest coordinated engineering projects in human history. The lasers would need to be phase-coherent, synchronized so precisely that their combined beam remains focused on a target thousands of kilometers away for the duration of the acceleration phase. Thermal management alone preventing the array from destroying itself with its own waste heat, is a formidable challenge. The sail itself would need to be perhaps a few meters across but only a few hundred atoms thick, thinner than anything we have ever manufactured at scale. It would need to reflect the laser light with near-perfect efficiency, because any absorption of that light would vaporize the sail instantly. It would also need to survive the interstellar medium, the sparse but real stream of gas and dust that fills the space between stars. At 20% of the speed of light, even a single hydrogen atom hitting the spacecraft carries significant kinetic energy. Over 4 light-years of travel, the cumulative bombardment of interstellar particles represents a genuine threat to the integrity of any material we know of. Researchers have proposed solutions, shaped nose cones of beryllium or other hard materials, erosion-resistant coatings, strategic orientation of the spacecraft during transit. None of these solutions have been tested in anything resembling actual interstellar conditions, because no such conditions exist within any distance we can currently reach. They are modeled, estimated, extrapolated. Whether they work in practice remains genuinely unknown. And then there is the question of what the spacecraft can actually carry. At gram scale, the mass of a large paperclip, the scientific payload is almost unimaginably small. Miniaturized cameras, basic spectrometers, perhaps a simple magnetometer. No telescopes with meaningful resolving power. No laboratory for analyzing chemical samples. Certainly no human beings. Breakthrough Starshot in its current conception would tell us something about Proxima Centauri, but not everything. It would be, in the language of planetary science, a flyby mission, the lowest tier of direct exploration, below orbital insertion, below landing, below sample returns still. A flyby of Proxima Centauri, with even a simple camera and spectrometer, would represent a leap in our knowledge of that system so vast that it barely fits in the same category as everything we currently know. What other proposals exist? Because breakthrough Starshot is not the only serious concept on the table. Nuclear pulse propulsion has been studied seriously since the 1950s. Project Orion, developed at the Los Alamos National Laboratory and later at General Atomics, proposed a spacecraft propelled by a series of nuclear explosions detonating behind a massive steel pusher plate. The spacecraft would absorb the shock of each explosion through a system of enormous shock absorbers, and the cumulative impulse of thousands of sequential blasts would accelerate it to velocities far beyond anything chemical propulsion can achieve. Theoretical calculations for advanced versions of this concept suggest velocities of several % of the speed of light, enough to reach Proxima Centauri in a few centuries rather than tens of thousands of years. Project Daedalus, developed by the British Interplanetary Society in the 1970s, proposed a variant using nuclear fusion rather than fission, specifically the detonation of small pellets of deuterium and helium-3 in a magnetic confinement chamber, producing a directed exhaust of superheated plasma. Daedalus was designed as an unmanned probe, roughly 18 meters across, capable of reaching 12% of the speed of light. The journey time to Proxima Centauri, approximately 50 years, the follow-on study, Project Icarus, updated the Daedalus design with modern physics and engineering knowledge. It remains a theoretical exercise. No fusion pulse drive has ever been built, and helium-3, the fuel Daedalus required, is extraordinarily rare on Earth, though it exists in larger quantities on the surface of the Moon and in the atmospheres of the gas giants. But the physics, unlike chemical propulsion, does not present an obvious thermodynamic wall. Fusion-based propulsion, if it were ever mastered, could in principle move large payloads, including theoretically crewed spacecraft, across interstellar distances within human-relevant timescales. There is a more speculative but scientifically grounded concept called the magnetic sail or mag sail. in which a superconducting loop generates a magnetic field large enough to interact with the interstellar medium and provide both propulsion from the stellar wind of the departure star and deceleration from the interstellar medium at the destination. The deceleration problem is perhaps the most underappreciated challenge in interstellar travel discussions. Getting up to speed is hard. Slowing down at the other end, without any infrastructure waiting for you at the destination, is arguably harder. A spacecraft arriving at Proxima Centauri at 20% of the speed of light and unable to decelerate would blow through the system in hours and continue into the void beyond, its mission reduced to a brief, spectacular flyby that was never intended to stop. Crude interstellar missions introduce a layer of difficulty so profound that most serious engineering studies treat them as a separate category entirely. The human body was not designed for interstellar space. Radiation alone, the cosmic ray flux of interstellar space, augmented by the relativistic blue shifting of incoming particles at high velocities, would deliver a cumulative dose to any unshielded crew that would be lethal within years. Shielding against cosmic rays requires mass, lots of it. A water shield thick enough to meaningfully attenuate cosmic rays would itself add enormous mass to the spacecraft, increasing the propulsion requirements in a feedback loop that drives the engineering toward the catastrophically impractical. Then there is the biology of isolation, of confinement, of generational psychology for a mission spanning centuries. If a ship traveling at 1% of the speed of light departs for Proxima Centauri, the people who arrive will be the great-great-great-grandchildren of the people who left. They will have been born, lived their entire lives, and grown old in a vessel with no possibility of return. They will arrive at a world that no human eye has ever seen up close, with whatever knowledge, culture, and mental health their multi-generational community managed to preserve across the voyage. The social engineering of such a mission, the governance, the psychology, the maintenance of technical knowledge across generations with no external reference or resupply, may be as difficult as the physics. Perhaps more so, relativistic effects begin to matter meaningfully at velocities above roughly 10% of the speed of light. At 20%, the breakthrough Starshot target, time dilation is modest but real. A clock on the spacecraft would run approximately 2% slower than a clock on Earth. At higher fractions of the speed of light, the effect becomes dramatic. A crew traveling at 90% of the speed of light would experience the journey to Proxima Centauri in less than 2 years of subjective time, while approximately 4.7 years passed on Earth. At 99%, the subjective journey time drops below 8 months. This is not science fiction. It is a direct consequence of special relativity, confirmed experimentally in particle accelerators and with atomic clocks on aircraft. The implication is that if humanity ever solves the propulsion problem, if fusion drives or laser sails or some technology not yet imagined allow travel at relativistic velocities, the interstellar journey becomes survivable within a single human lifetime. The catch is the energy required. Accelerating a crewed spacecraft of any meaningful mass to 90% of the speed of light requires energy outputs that dwarf the total current energy production of human civilization by factors that are genuinely difficult to express without scientific notation. We are not there. We may not be there for centuries, but we were not always capable of crossing oceans either. There is something important in that parallel, and something important in its limits. The ocean crossing analogy is seductive but imperfect. The Pacific Ocean is approximately 17,000 kilometers wide. Proxima Centauri is approximately 40 trillion kilometers away. The ratio of those distances is not a matter of degree, it is a difference in kind. The oceans could be crossed with technology that was recognizably an extension of existing craft. Bigger ships, better navigation, more supplies. The interstellar gulf requires physics that we have not yet harnessed, at scales we have not yet demonstrated, sustained for timescales that exceed anything in our engineering experience. And yet, and this is what serious people, thinking carefully about the long arc of human capability, keep coming back to, the physics does not say no, it says hard, it says expensive, it says not yet, but it does not say never. Every generation that has inherited this question has also inherited better tools for thinking about it, better telescopes, better understanding of the interstellar medium, better physics, better materials science. The generation that actually solves interstellar propulsion, if it comes, will likely look back at our current debates the way we look back at early aviation pioneers arguing about whether heavier-than-air flight was theoretically possible. They were right that it was possible. They were just working with wood and canvas. We are still, in the cosmic sense, working with wood and canvas. And perhaps that is the most clarifying thought of all. Not discouraging, clarifying. Because it tells us exactly where we are in the story, not at the end, not even close to the middle. We are in the earliest chapters, the ones where the characters are still figuring out that there is a journey to be made, that the destination is real, and that the distance, however vast, is finite. Proxima Centauri is 4.24 light-years away. It has always been 4.24 light-years away. It will be there, burning its slow red fire for 4 trillion years. We have time. What we do with that time, the science we build, the propulsion we develop, the telescopes we launch, is Part 7's territory, because before anything physical crosses that gulf, something else will, information. And the story of what we might learn about Proxima b from right here, without ever leaving Earth's neighborhood, is more surprising and more profound than most people realize. We don't have to go there to know it. That sounds like a contradiction. 4.24 light-years of empty space, and we can know something real and specific about what exists on the other side of it, without leaving, without sending so much as a probe? Yes, and the science behind how is one of the most quietly revolutionary developments in the history of astronomy. It begins with light. Everything we know about the universe beyond our solar system, every exoplanet discovered, every stellar composition mapped, every galaxy whose distance and velocity we have measured, comes to us through light. Electromagnetic radiation, traveling across space at the universal speed limit, carrying encoded within its spectrum an extraordinary amount of information about the object that emitted or reflected it. The key tool is spectroscopy. When light passes through a gas, any gas, the atoms and molecules in that gas absorb specific wavelengths. Each molecule has a unique absorption signature, a fingerprint of missing colors that it removes from the light passing through it. Water absorbs at certain wavelengths, carbon dioxide absorbs at others, methane, ozone, nitrous oxide, oxygen, each has its own distinct pattern. When starlight passes through a planet's atmosphere during a transit, when the planet crosses in front of its star as seen from our vantage point, a tiny fraction of that starlight filters through the atmospheric rim of the planet. The spectrum of that filtered light, compared to the spectrum of the star alone, reveals what molecules are present in the atmosphere. This technique is called transmission spectroscopy, and it is currently the most powerful tool we have for characterizing exoplanet atmospheres. JWST has already demonstrated its extraordinary capability in this area, detecting carbon dioxide, sulfur dioxide, water vapor, and other molecules in the atmospheres of planets dozens to hundreds of light-years away. The sensitivity of JWST's instruments is such that it can detect molecular abundances at the level of parts per million in the atmospheres of worlds it will never visit. Now here is the critical question for Proxima b. Does it transit its star? A transit occurs when a planet's orbital plane is aligned nearly edge-on to our line of sight. so that, from Earth, the planet passes across the face of the star. This alignment is a matter of geometry and chance. For a planet at Proxima B's orbital distance from its star, the probability of a favorable transit geometry is approximately 1.5%, low but not negligible. Observations with the Spitzer Space Telescope and ground-based photometric campaigns have searched for transits of Proxima B and have not detected them. The current scientific consensus is that Proxima B most likely does not transit its star as seen from Earth. This is a genuine obstacle. Without a transit, transmission spectroscopy, our most sensitive technique for atmospheric characterization, cannot be directly applied to Proxima B using current instruments, but transit spectroscopy is not the only path. There is a technique called direct imaging spectroscopy, in which a telescope equipped with a coronagraph, a device that blocks the overwhelming light of the central star, attempts to capture the faint reflected light of a planet directly. Once that reflected light is isolated, its spectrum can be analyzed for atmospheric signatures. This is far more technically demanding than transit spectroscopy. The contrast ratio between a star and an Earth-sized planet in reflected light is roughly 10 billion to 1, blocking the star's light precisely enough to reveal the planet beside it, without losing the planet's signal in the residual glare, requires optical precision at a level that pushes the limits of current engineering. But Proxima Centauri is our nearest stellar neighbor. That proximity is a profound advantage. The angular separation between Proxima b and its star, as seen from Earth, is approximately 37 milliarcseconds at maximum elongation. That is tiny by everyday standards, but by the standards of direct imaging, it is among the most favorable geometries of any known exoplanet. For a telescope with sufficient aperture and coronagraphic capability, Proxima b is one of the highest priority targets precisely because of its proximity. The extremely large telescope, the ELT, currently under construction on Cerro Amazonas in the Atacama Desert of Chile, will be the largest optical telescope ever built when it sees first light, expected in the late 2020s. Its primary mirror will be 39 meters across, nearly 4 times the diameter of the largest existing optical telescopes. Combined with its planned high-contrast imaging instruments, including METIS and Harmony, the ELT is specifically identified in its science case documentation as capable of attempting direct imaging of Proxima b. Not guaranteed, not easy, but within the realm of physical possibility for that instrument, and you don't need a 39-meter mirror to start exploring the sky. The Celestron StarSense Explorer telescope fits in your living room and works with your phone. The link is in the description and pinned on the comments. But what would a detection look like? Not a photograph in any conventional sense. At the distances and angular scales involved, Proxima b would appear as a single point of light, a pixel at best, separated from its star by an amount that the telescope's coronagraph would need to cleanly resolve. But that single pixel of reflected starlight dispersed through a spectrograph would yield a spectrum, and that spectrum, analyzed for the presence or absence of specific molecular signatures, would tell us more about the nature of that world than any other measurement currently conceivable from Earth. What would we look for? The biosignature combinations, methane and carbon dioxide without carbon monoxide, nitrous oxide at unexpectedly high concentrations, the simultaneous presence of oxygen and a reducing gas like methane that would rapidly destroy each other in the absence of a continuous biological source, but there are subtler signatures as well. The presence of a surface ocean would imprint a specific glint, a directional brightening of the reflected light at certain geometries that has been theoretically modeled and would, in principle, be detectable with sufficient sensitivity. Vegetation, if it exists in any form analogous to Earth's, might produce a spectral edge in the near-infrared, a sharp increase in reflectivity at wavelengths just beyond the red end of the visible spectrum, known as the red edge, which on Earth is caused by the cellular structure of plant leaves and is detectable in Earth's disk-averaged spectrum from space. These are all theoretically present in the light that Proxima b already reflects. Right now, as you listen to this, traveling toward us across 4.24 light-years of space, arriving at Earth diluted and mixed with the overwhelming flood of Proxima Centauri's own light. The information is in the photons. It has always been there. We simply haven't yet built instruments sensitive enough to pull it out cleanly. The Habitable Worlds Observatory, a space telescope concept currently in the advanced planning phase at NASA, recommended as a high priority by the 2021 Decadal Survey on Astronomy and Astrophysics, is specifically designed for this purpose. A 6-meter class space telescope with an internal coronagraph optimized for directly imaging Earth-like planets around nearby Sun-like stars, the Habitable Worlds Observatory is projected for launch in the late 2030s to early 2040s. Its target list includes the nearest and most favorable nearby star systems. While its primary targets are Sun-like stars because their habitable zones are more easily separated from the stellar disk in angular terms, the science case includes observations of nearby red dwarfs. Proxima Centauri is 4.24 light-years away. No other known star with a confirmed planet in or near its habitable zone is closer. Whatever generation of telescope finally achieves the sensitivity to characterize Proxima b's atmosphere, that world will be near the top of every observation queue, because no other target offers the same combination of proximity and planetary interest. There is another detection pathway that is less discussed but worth understanding: atmospheric escape. When a planet loses its atmosphere to stellar wind and radiation, a process we know is significant at Proxima b's orbital distance, the escaping gas forms a diffuse envelope around the planet that can, in some cases, be detected in ultraviolet observations. Observations of Proxima b using the Hubble Space Telescope have searched for signs of hydrogen escape, a proxy for water loss, and while the results have been inconclusive, the technique itself is real and has successfully detected atmospheric escape at other close-in planets around active stars. Future ultraviolet-capable space telescopes could, in principle, detect the signature of an atmosphere in the process of being stripped, telling us not just what is present, but how quickly the planet is losing it. All of this, the ELT, the Habitable Worlds Observatory, the ultraviolet searches, the coronagraphic imaging, points toward a window, a period, perhaps within the next 2 to 3 decades, in which humanity's observational capability crosses a threshold beyond which Proxima b is no longer simply a minimum mass lower bound on a radial velocity curve. It becomes a characterized world, a place with a known atmosphere or a known lack of one, a place where the presence or absence of biology is at least constrained, if not confirmed. That crossing, that threshold, will be one of the defining moments of scientific history, regardless of what it reveals. Because even a definitive non-detection, a spectrum that shows a bare rock with no atmosphere, or a Venus-like hellscape of carbon dioxide and sulfuric acid, tells us something of enormous value. It tells us what Proxima b is not, and in science, knowing what something is not is often the necessary precondition for eventually knowing what it is. But there is a result, one specific observational outcome, that would not merely advance science. It would rupture it. It would split the history of human knowledge into 2 epochs, before and after. A spectrum of Proxima b's atmosphere showing the simultaneous presence of oxygen and methane, or nitrous oxide at biological abundances, or the red edge of vegetation. or some combination of chemical disequilibrium so pronounced that no geological or photochemical model can plausibly explain it without invoking biology. That result, those photons, after traveling 4.24 light-years, entering a telescope mirror on Earth or in orbit, being dispersed through a spectrograph and recorded on a detector, would be the moment our species learned that we are not alone. That life, in whatever form it takes on that distant, tidally locked, radiation-battered world, has found a way, and the silence that would follow, the quiet moment before the world fully understood what had been found, would be unlike anything in human experience. Astronomers have thought about this, philosophers have thought about it, theologians and policymakers and psychologists have thought about it. The SETI post-detection protocol, a framework developed over decades for how the scientific community should handle and communicate a confirmed detection of extraterrestrial life, exists precisely because thoughtful people recognize that the moment is not purely theoretical. It is possible, it may be approaching, and humanity, collectively, has not spent nearly enough time preparing for what it would mean for religion, for philosophy, for our understanding of our own uniqueness, our own significance, our own loneliness in the cosmos, for the political and cultural frameworks we have built on the implicit assumption, never stated, never examined, just assumed, that we are the only minds the universe has produced. Those questions don't have clean answers, they probably can't. But the fact that we are close enough, technologically, observationally, scientifically, that we need to start thinking about them seriously is itself one of the most remarkable facts about the moment in history we currently occupy. We are the first generation of humans for whom the detection of life on another world is not purely a thought experiment. It is a near-term observational possibility, and Proxima Centauri, that faint, red, furious star 4.24 light-years from your front door, is at the center of it. If you are still watching, then this channel was made for you. Don't forget to hit subscribe and give this video a like. Every video this channel goes deeper into the questions that matter most and brings you back changed. There is a question that doesn't get asked enough in science communication. Not what did we discover or how does it work, but something quieter and more personal than either of those. What does it do to you to actually know this, not to hear it as a fact, not to nod along to a documentary and forget it by morning, but to genuinely sit with the reality that there is a star 4.24 light-years from Earth, that it has at least one planet in its habitable zone, that the physics of that planet's situation are both deeply familiar and profoundly alien, and that within your lifetime, not in some distant imagined future, but within the span of years, you are likely to actually live. We may know whether that world is alive. What does that knowledge do to a person? Because it does something, it has always done something, to the people who sit with it long enough. The astronomers and astrobiologists who spend their careers thinking about these questions are not unchanged by them. The philosophers who have grappled seriously with the implications of extraterrestrial life, not as science fiction, but as a genuine near-term possibility, describe a kind of cognitive vertigo, a sense that the ground shifts slightly underfoot when you truly absorb what the universe is telling you. And what it is telling you is this: you are small, cosmically, almost absurdly small. The Earth is a pale blue point, orbiting an unremarkable star in the outer edge of a galaxy containing somewhere between 100 billion and 400 billion other stars. That galaxy is one of at least 2 trillion galaxies in the observable universe. The scales involved, spatial, temporal, energetic, are so far beyond human intuition that our brains, shaped by hundreds of thousands of years of evolution on the African savanna, genuinely cannot process them directly. We handle them mathematically, we represent them in models. but we don't feel them the way we feel the warmth of sunlight or the weight of a stone in our hand. And yet, and this is the part that matters, smallness is not the same as insignificance. This distinction is one of the oldest and most important in philosophy, and it becomes newly urgent when you look at it through the lens of modern cosmology. The universe is vast, it is ancient. It operates according to physical laws that show no particular preference for the existence of minds, the emergence of consciousness, of self-awareness, of the capacity to ask questions about the nature of reality, is not written into the laws of physics as a guaranteed outcome. It appears to be a contingent fact, something that happened here through an extraordinarily long and improbable chain of events, and may or may not have happened elsewhere. That contingency, that sense that minds are not inevitable, but rather fragile and precious outgrowths of matter that became complex enough to contemplate itself, is one of the most powerful arguments for taking our own existence seriously, not in a self-congratulatory way, not as an excuse for arrogance, but as a reason for genuine awe at the fact that the universe, through you, is looking at itself. Carl Sagan said it plainly: "We are a way for the cosmos to know itself." That sentence has been quoted so many times that it risks losing its force. But it is worth recovering, because what it describes is not poetry. It is a literal statement of physical fact. The atoms in your body were forged in the cores of stars that lived and died before our sun existed. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was synthesized in stellar furnaces across billions of years of cosmic history and scattered across the galaxy by supernovae. You are not separate from the universe, observing it from outside. You are a part of it that has become organized enough to observe itself. And the question of whether Proxima b is alive, whether the atoms in that world have also organized themselves into something that metabolizes, replicates, evolves, perhaps eventually thinks, is a question about how widespread that process of self-organization actually is. Whether consciousness and life are rare accidents or something the universe does routinely, given time and the right conditions, that question has no clean answer yet. But the fact that we are asking it, with real telescopes, real physics, real data, is itself one of the most extraordinary things that has ever happened in the 14 billion-year history of this universe, as far as we know. And that qualifier, as far as we know, is doing a lot of work, because it gestures toward the other possibility, the one that changes everything if it turns out to be true. What if we are not alone in asking? What if somewhere in the universe, perhaps not at Proxima Centauri, perhaps somewhere far more distant, but somewhere real, there is another mind looking out at the cosmos and asking the same questions? Another civilization that has traced the same path from chemistry to biology to consciousness, that has built its own instruments, that has looked in our direction and wondered about the unremarkable yellow star and the small blue world orbiting it. The SETI program, the search for extraterrestrial intelligence, has been listening for artificial signals from space for more than 60 years. Radio signals, laser pulses, any pattern that bears the signature of intentional transmission rather than natural process. In 60 years of searching, with instruments of steadily increasing sensitivity, the answer has been silence. Qualified silence. We have not searched comprehensively, we have not listened on all frequencies, we have not monitored all stars for all possible signal types, but silence nonetheless. The most famous anomaly in SETI history is the WOW signal, detected in 1977 by astronomer Jerry Eman at the Big Ear Radio Telescope at Ohio State University. It was a narrowband radio signal lasting 72 seconds at a frequency close to the hydrogen line, the frequency that many theorists had predicted an intelligent civilization might choose for interstellar communication, precisely because Hydrogen is the most abundant element in the universe, and its spectral line would be known to any technologically capable species. The signal was so striking that Eamon circled it on the printout and wrote "Wow" in the margin. It has never been detected again. Its origin remains unexplained. It was almost certainly not extraterrestrial intelligence. The most likely explanations involve natural astrophysical sources or terrestrial interference, but it has never been definitively ruled out, and it remains, after nearly 5 decades, a data point that resists full explanation. More recently, the Breakthrough Listen initiative, the most comprehensive SETI program in history, funded by Yuri Milner with $100 million over 10 years and using the world's largest radio telescopes, has conducted systematic observations of nearby stars, including Proxima Centauri. In 2020, a narrowband radio signal designated BLC-1 was detected appearing to originate from the direction of Proxima Centauri during Breakthrough Listen observations with the Parkes telescope in Australia. The signal briefly generated significant excitement within the astronomical community. It was subsequently determined, after careful analysis, to be radio frequency interference, almost certainly of human origin, a signal produced by technology on or near Earth that happened to appear in the data during observations of Proxima Centauri. The investigators were transparent about this conclusion. It was not extraterrestrial. But the episode illustrated something important. The instruments are now sensitive enough that a genuine signal, if one existed, would be detectable. The search is no longer purely theoretical, it is operational. If there is something at Proxima Centauri with the capability and intention of transmitting, something technological, something deliberate, Breakthrough Listen would have a reasonable chance of detecting it. The fact that nothing has been found is itself meaningful data. It constrains what can exist there. It doesn't rule out life. It doesn't even rule out intelligence. But it rules out a civilization actively and powerfully broadcasting in our direction on radio frequencies. What it cannot rule out is a civilization that is not broadcasting, one that has no radio technology, one that uses communication methods we haven't thought to look for, one that is there, in whatever form life at Proxima Centauri might take, simply living, without any awareness or interest in the pale yellow star 4.24 light-years away, and the curious, small-brained primates who evolved there and started pointing telescopes at the sky. The universe does not owe us contact. It does not owe us signals. It does not owe us confirmation that we are not alone. The silence may simply be the silence of vast distances and incompatible technologies and civilizations that never developed radio because their electromagnetic environment made it impractical, or that developed it and moved past it before they thought to look in our direction. Or the silence may mean something darker, something the great filter argument gestures toward without being able to specify. Something that waits for every technological civilization at some point in its development, patient and indifferent, in the same way that physics itself is patient and indifferent. This is, genuinely, one of the open questions of our time. Not a rhetorical open question, one that sounds deep but has an obvious answer, a real one, an empirically unresolved one. A question whose answer, when it comes, will change everything. And in the meantime, in the years and decades while the telescopes are being built and the spectra are being gathered and the data is being analyzed, there is something valuable in sitting with the uncertainty itself, in resisting the urge to collapse it prematurely into either comfortable optimism or resigned pessimism. The universe is under no obligation to be either full of life or empty of it. It is what it is. And we are still just barely beginning to develop the tools to find out which. What we can say with confidence is that the asking matters, that a species capable of formulating these questions and building instruments to answer them has done something genuinely remarkable, that the 14 billion years of cosmic history that preceded this moment, the stars that lived and died, the supernovae that scattered their elements, the molecular clouds that collapsed into new solar systems, the chemistry that eventually kindled into biology, on at least one small world, all of it led here. To this question, to this search, and Proxima Centauri, 4.24 light-years away, burning its slow red fire, orbited by at least one world that may or may not carry the signature of life, sits at the center of that search, not because it is the only candidate, but because it is the nearest one, because it is the place where the question is most likely to be answered first, because the photons from that world, carrying whatever information they carry, arrive here continuously, have been arriving for as long as Earth has existed, and we are finally, just now, learning to read them. Science doesn't happen in the abstract. It happens in specific places, with specific instruments built by specific people who spent years of their lives making them work. And the science of Proxima Centauri, the actual, concrete, near-future effort to understand that world, is more advanced, more organized, and more imminent than most people realize. Let's talk about what is actually coming. Not speculation, not hopeful extrapolation. The real pipeline of missions, telescopes, and observational campaigns that are either already underway or in advanced development right now, and what each of them could tell us about the nearest star system to our own. Start with what is already in space and already working. JWST, the James Webb Space Telescope, has been operational since 2022, and its impact on exoplanet science has already exceeded the expectations of even its most optimistic advocates. Its near-infrared spectrograph, known as NIRSpec, and its mid-infrared instrument, MIRI, are capable of characterizing the atmospheres of transiting exoplanets with a sensitivity that no previous telescope could approach. JWST has already detected carbon dioxide, sulfur dioxide, and water vapor in exoplanet atmospheres at distances of dozens to hundreds of light-years. It has detected silicate clouds on a gas giant. It has begun probing the atmospheres of rocky, Earth-sized planets in the TRAPPIST-1 system, 7 worlds orbiting an ultra-cool red dwarf about 40 light-years away, 3 of which sit within the habitable zone. The TRAPPIST-1 results are directly relevant to Proxima b. TRAPPIST-1 is a red dwarf, similar in many respects to Proxima Centauri, though somewhat cooler and less active. Its planets, unlike Proxima b, do transit their star as seen from Earth, which means JWST can observe them in transmission spectroscopy, gathering their atmospheric spectra directly. Early JWST results on TRAPPIST-1e, F, and G, the 3 habitable zone worlds, are expected to accumulate over the coming years. What those spectra show will be one of the most closely watched results in the history of astronomy. If any of the TRAPPIST-1 habitable zone planets show signs of a substantial atmosphere, let alone biosignatures, the implications for Proxima b and for red dwarf habitability generally will be profound, because TRAPPIST-1 and Proxima Centauri are not identical, but they are related, both members of the red dwarf family, both capable of hosting rocky worlds in their habitable zones, both presenting the same fundamental tension between the long-term stability of a cool, dim star and the short-term violence of its flares and stellar wind. Whatever JWST learns about the atmospheres of TRAPPIST-1's planets is a preview, imperfect but informative, of what we might eventually learn about Proxima b. JWST is not expected to directly characterize Proxima b's atmosphere. The geometry doesn't favor it. Proxima b almost certainly doesn't transit. But JWST's work on the TRAPPIST system, on other nearby red dwarf planets, and on the general relationship between red dwarf activity and atmospheric survival is building the scientific framework within which any future Proxima b observation will be interpreted. Now move to what is being built on the ground. The extremely large telescope, which we discussed in Part 7, is the centerpiece of the next generation of ground-based astronomy. 39 meters of primary mirror, adaptive optics systems capable of correcting for atmospheric turbulence in real time with extraordinary precision, and a suite of instruments designed specifically for high-contrast imaging and spectroscopy of nearby exoplanets. First light is currently anticipated in the late 2020s, with full science operations ramping up in the early 2030s. One of the ELT's instruments, called ANDES, the Amazones High Dispersion Echelle Spectrograph, is specifically designed for high-resolution spectroscopy of nearby exoplanets in reflected light. Its science case explicitly includes the direct detection and atmospheric characterization of Proxima b. ANDES would be capable of detecting oxygen, water vapor, and potentially other atmospheric components in Proxima b's reflected starlight, if the planet has sufficient atmosphere and if the instrument achieves its design sensitivity. These are significant ifs, but they are engineering ifs, not physics ifs. The fundamental science permits it. Whether the hardware delivers at its design specification is a question that will be answered in the early to mid-2030s alongside the ELT. Two other massive ground-based telescopes are in development. The 30-meter telescope, planned for Mauna Kea in Hawaii, and the Giant Magellan telescope, under construction at Las Campanas Observatory in Chile. Both will have capabilities broadly comparable to the ELT in relevant respects, though differing in specific instrument suites and design choices. The simultaneous operation of three extremely large telescopes in the 2030s, two in Chile, one in Hawaii, will represent an observational capability for nearby exoplanet characterization that is qualitatively different from anything that has existed before. Different targets can be observed simultaneously from different hemispheres. Detections can be cross-confirmed. Systematic errors that might fool a single telescope can be identified by the disagreement between independent instruments. This matters enormously for biosignature detection. The history of science is littered with results that seemed robust on a single instrument and turned out to be instrumental artifacts. The simultaneous availability of multiple independent, extremely large telescopes means that a claimed biosignature detection in Proxima b's atmosphere, if one were made, could be verified or refuted by independent observation within months. The scientific community would not have to wait years for a second telescope to be built. The infrastructure for confirmation will already exist. In space, the Roman Space Telescope, formerly known as WFIRST, is NASA's next major space observatory, currently in advanced development with a launch target in the mid-2020s. Roman is primarily a wide-field survey telescope designed to map hundreds of millions of galaxies for cosmological studies and to conduct a statistical census of exoplanets via gravitational microlensing. But it also carries a coronagraph instrument, a high-contrast imaging system that, while not the primary science driver of the mission, is explicitly described as a technology demonstration for future direct imaging telescopes. Roman's coronagraph is expected to be the most capable space-based coronagraph ever flown, and its performance data will directly inform the design of the Habitable Worlds Observatory. The Habitable Worlds Observatory, recommended as the highest priority large space mission by the 2021 Decadal Survey, is the instrument that could change everything. A roughly 6-meter class space telescope with a sophisticated internal coronagraph designed specifically to image and spectroscopically characterize Earth-like planets in the habitable zones of nearby stars. Its target list, as currently conceived, focuses primarily on Sun-like stars because the habitable zones of Sun-like stars are at angular separations more favorable for coronagraphic imaging than the tightly packed habitable zones of red dwarfs. But Proxima Centauri's extreme proximity partially compensates for this geometric disadvantage. Proxima b's angular separation from its star at maximum elongation, roughly 37 milliarcseconds, is small, but it may fall within the inner working angle of the Habitable Worlds Observatory's coronagraph for some design configurations. The mission's science team has discussed Proxima b as a potential target, and the final instrument design choices will determine whether it is accessible. Current planning timelines place the Habitable Worlds Observatory launch somewhere in the late 2030s to early 2040s. That is a long time, but it is not an unimaginably long time. A child born today will be in their 20s when that telescope launches. The scientists who are graduate students right now, learning spectroscopy and coronagraph design and atmospheric modeling in universities around the world, will be at the peak of their careers when that telescope begins returning data. This is one of the most clarifying ways to think about the timeline. The discovery of whether Proxima b is alive, if it is going to be made from Earth or Earth orbit using current technological trajectories, will be made by people who are alive today. Some of them are already working on the problem. Some of them are in school. Some of them haven't yet decided to become astronomers, but will. Beyond these flagship missions, there is a growing ecosystem of smaller, more targeted efforts that deserve mention. The Toliman mission, a small space telescope designed specifically to perform precision astrometry of the Alpha Centauri system, searching for the gravitational wobble of planets around Alpha Centauri A and B, was developed by a team led by astronomer Eduardo Bendek and supported by the Breakthrough Initiatives. Astrometry, the precise measurement of a star's position on the sky over time, can detect the gravitational tug of an orbiting planet in a way that complements the radial velocity technique. For nearby stars like those in the Alpha Centauri system, astrometry becomes increasingly powerful, precisely because of the system's proximity. Toliman is a targeted, focused mission with a specific scientific objective, and its results, if successful, would expand our planetary census of our nearest stellar neighbors beyond what radial velocity alone can achieve. There is also the ongoing work of ground-based radial velocity campaigns. The Espresso spectrograph on the Very Large Telescope in Chile, one of the most precise radial velocity instruments ever built, continues to monitor Proxima Centauri and other nearby stars, searching for additional planets and refining the orbital parameters of known ones. In 2020, an Espresso analysis of existing radial velocity data identified a candidate second planet in the Proxima Centauri system, designated Proxima c, at a much larger orbital distance, beyond the habitable zone, with an orbital period of approximately 5 years. The status of Proxima c remains under investigation. Subsequent analyses have debated its reality, and it has not yet achieved confirmed planet status. But its candidacy illustrates that Proxima Centauri's planetary system may be more complex than a single close-in world, and that continued radial velocity monitoring is still producing new discoveries in our nearest stellar neighborhood. The aggregate picture that emerges from all of this is one of accelerating momentum. Each instrument builds on the last. Each detection, even a non-detection, even a constrained upper limit on atmospheric composition, narrows the space of possibilities and focuses subsequent observations. The science of Proxima Centauri is not static. It is a rapidly moving frontier, advancing on multiple fronts simultaneously, driven by a global community of researchers who share, beneath the technical diversity of their specific projects, a common underlying question: is there life out there? And in the specific case of Proxima b, is there life there? 4.24 light-years away, orbiting that red, flickering ancient star, on a world that is tidally locked and radiation bathed and gravitationally stressed and chemically complex in ways we are only beginning to understand. The answer, when it comes, will not arrive with fanfare. It will arrive as data, as a spectrum, as a set of numbers in a file on a computer in an observatory control room, processed by a pipeline, analyzed by a team, debated at a conference, submitted to a journal, reviewed by peers, revised and resubmitted, and eventually published. Science does not announce itself with trumpets. It accumulates quietly, one measurement at a time, until the accumulation becomes undeniable. But the moment, the specific moment, when a scientist looks at a spectrum of Proxima B's atmosphere and sees something that cannot be explained without biology, that moment will be unlike any other in the history of human knowledge, and unlike the discoveries of the past, which were made before the world was watching. This one will happen in an era of instant global communication. Everyone will know, almost simultaneously. The data will be public, the analysis will be streamed, the confirmation will be crowdsourced by thousands of independent researchers within hours. That moment is not guaranteed. The spectrum might show a bare rock. It might show a carbon dioxide atmosphere with no signs of biology. It might be ambiguous, suggestive but not conclusive, requiring decades more observation to resolve. Science rarely delivers clean endings. It delivers better and better approximations of the truth, each one more constrained than the last, each one pointing more clearly in a direction that eventually becomes undeniable. But the direction we are pointing in right now, the trajectory of telescopes and instruments and observational campaigns described in this part, is toward an answer, a real answer, about a real world. Around a real star, we have come a long way together from the surface of a tidally locked world, half frozen and half scorched, caught in the grip of a star so close it fills the sky like a bruise. Through the physics of stellar flares and atmospheric stripping, through the deep chemistry of life's origins and the staggering improbability of complexity, through the engineering of laser sails and fusion drives and the brutal mathematics of interstellar distance, through the quiet, accumulating science of telescopes that are learning, slowly and painstakingly, to read the light of another world. We have arrived now at the question underneath all the other questions, the one that the science points toward but cannot itself answer, the one that belongs not just to astronomy or biology or engineering, but to something older and more fundamental, something that has been with us since the first human being looked up at a night sky and felt, simultaneously, the vertigo of vastness and the stubborn insistence of curiosity. What does it mean? Not what does Proxima B mean scientifically. We've covered that. What does this entire endeavor mean? This species-wide effort to understand our place in a universe so large it defeats comprehension, to find out whether the chemistry that kindled into life on this small world has done so anywhere else, to reach, with telescopes and mathematics and sheer intellectual stubbornness, across distances that no human body has ever crossed or likely ever will. What does it mean that we ask at all? There is a version of this question that collapses quickly into nihilism. The universe is vast. We are tiny. Whatever we discover about Proxima B will not change the price of groceries or resolve any political conflict or extend a single human life by a single day. In the face of 4 trillion years of red dwarf burning and 2 trillion galaxies wheeling through the void, the distinction between a world that harbors life and one that doesn't seems, from a certain angle, almost trivially small, but that angle is wrong. And it is wrong in a way that is worth being precise about. The universe does not assign meaning. It never has. The stars don't care whether Proxima B is alive. The laws of physics are indifferent to whether any mind ever arose to comprehend them. The cosmos has no investment in our curiosity, no preference for our survival, no stake in whether the questions we are asking get answered. And yet here we are, asking them. That fact, that consciousness arose in this universe and turned its gaze outward and began, systematically and relentlessly, to demand that the cosmos account for itself, is not a small thing. It may be the most significant thing that has ever happened in 14 billion years of cosmic history, because for all that time, the universe existed without being known. Galaxies formed and merged and scattered. Stars lived and died and seeded new generations with their remnants. Planets cooled and oceans formed and chemistry stirred. All of it happened in a kind of cosmic silence, not silence in the acoustic sense, but in a deeper sense. The silence of process without witness, event without understanding, existence without meaning. And then, on at least one small world, matter organized itself in such a way that it began to look back, to ask what it was made of, to trace its own origins, to wonder whether it was alone. That is what you are doing right now. Not passively absorbing information, actively participating in the oldest and most important project our species has ever undertaken. The project of understanding, the project of refusing to accept ignorance as a permanent condition, the project of reaching, always reaching, toward whatever is just beyond the current edge of knowledge. Proxima Centauri sits at that edge. It has sat there, unexamined, for the entire history of human civilization. Every philosopher who ever wondered about other worlds, every astronomer who ever mapped the sky, every person who ever lay on their back in a field at night and felt that particular mixture of smallness and wonder, all of them looked up at a sky that contained Proxima Centauri, without knowing it was there, without knowing it harbored at least one world in its habitable zone, without any of the tools we now have to begin understanding what that world actually is. We are the first generation for whom that ignorance is ending, not ended, ending. The process is underway. The telescopes are being built. The spectra are being gathered. The models are being refined. The answer, whatever it is approaching. It may take 10 years. It may take 30. It may, if the physics of direct imaging proves harder than current models suggest, take longer still. Science does not operate on schedules we find convenient. It operates on the schedules imposed by the difficulty of the problem and the ingenuity of the people working on it. But the direction is clear, and the direction is toward Proxima Centauri. Now, let's talk about what the answer might actually be. Not which answer is most likely, but what each possible answer means in the deepest sense for our understanding of where we are in the cosmic story. If Proxima b is a dead world, bare rock, no atmosphere, stripped clean by 4.5 billion years of stellar violence, then we will have learned something true and important and sobering. We will have learned that proximity to a red dwarf is genuinely hostile to planetary atmospheres in a way that current models may be underestimating. We will have a data point suggesting that the most common type of star in the galaxy may be an inhospitable host for the kind of surface habitability we associate with life. That would push our search outward, toward sun-like stars, toward worlds at greater distances, toward environments that more closely resemble the one we know produced life. It would narrow the universe of realistic candidates, at least for surface biospheres. It would not end the search, but it would reshape it. If Proxima b has a thick, barren atmosphere, carbon dioxide and nitrogen, geologically active but biologically empty, then we will have learned that atmospheres can survive around red dwarf planets, but that survival alone is not sufficient for life. We will have a Venus analogue around the nearest star, which is scientifically rich and philosophically neutral. It would tell us that the barrier to life is not purely atmospheric retention. It is something further along the chain: chemistry, liquid water stability, something we haven't fully identified yet. The search would continue, more informed than before. If Proxima b has a thin atmosphere with signs of water vapor but no biosignatures, a cold, dry world, perhaps partially habitable in theory but biologically quiet in practice, then we will be confronting the possibility that the origin of life, even given suitable conditions, is genuinely rare. That chemistry, left to itself under the right physical parameters, does not inevitably reach biology. That the spark, whatever it is, does not always catch. That finding the second example of life in the universe will require looking much further than 4.24 light-years. That result would be humbling in a specific way, not the humbling of smallness, but the humbling of loneliness, of being perhaps genuinely rare. And if Proxima B's spectrum shows the fingerprints of biology, if the methane and carbon dioxide ratios are wrong for geology, if oxygen sits alongside a reducing gas that should have destroyed it, if nitrous oxide appears at abundances that no known abiotic process can produce, if the red edge of something photosynthetic glints in the near-infrared, if any combination of signals points unmistakably toward a living world, then everything changes, not some things, everything. The entire framework within which our civilization understands itself, our religions, our philosophies, our sense of uniqueness, our implicit assumption that the story of life is the story of Earth, would need to be rewritten, not discarded, rewritten, extended. The discovery that life exists at Proxima Centauri would not invalidate any existing human belief system or cultural tradition, but it would demand that every one of them expand to accommodate a universe that is alive in more than one place, that the biology we know is not a cosmic anomaly but a cosmic pattern, that the universe, under the right conditions, does what it did here, and that realization that life is a pattern rather than an accident would transform every subsequent question we ask about the cosmos. It would make the search for intelligence more urgent, because if life is common, the probability of intelligence somewhere rises dramatically. It would reshape our understanding of our own evolutionary history, because a universe in which life arises readily is a universe in which the specific path life took on Earth, the specific chain of accidents and innovations and extinctions and survivors, is one of many possible paths, not the only one. It would make the great filter question more pressing, not less, because if the origin of life is not the filter must lie elsewhere, and we would need to find it. It would also, in a quieter and more personal way, change the experience of looking up at the night sky, because that faint red point of light, invisible to the naked eye, unremarkable even in a small telescope, easily overlooked in favor of more dramatic celestial objects, would no longer be just another star. It would be a neighbor, in the most meaningful sense of that word, a place where something lives, where chemistry has crossed the threshold into biology, where matter has organized itself into something that metabolizes and replicates, and perhaps, in the deepest and most uncertain reaches of speculation, experiences the universe in some way. The distance of 4.24 light-years would not shrink. It never does, but it would feel different. The void between us and Proxima Centauri, that unimaginable gulf of cold, radiation-threaded space, would no longer feel like emptiness. It would feel like separation, like the space between two lanterns in a very dark room, and that change in feeling, that shift from emptiness to separation, would be, in its own way, one of the most important events in human psychological and cultural history, because it would mean we are not alone, not in the abstract, statistical sense of surely there must be life somewhere in 2 trillion galaxies. In the specific, concrete, measurable sense of there is life at Proxima Centauri. We have seen its chemistry, we have read its atmosphere, we know it is there. What we do with that knowledge, how we respond as a civilization, what we prioritize, what we decide is worth building and launching and risking, will define the next chapter of the human story in ways that are genuinely impossible to predict. But the knowledge itself, once gained, cannot be ungained. It would be permanent, the second most important fact our species has ever learned after the fact of our own existence, so here is where we are. Proxima Centauri is 4.24 light-years away. It has at least one planet in its habitable zone. That planet faces conditions both deeply challenging and strangely familiar. The science of understanding it is advancing on multiple fronts simultaneously. The generation of humans who will answer the question of whether it is alive is already alive themselves, already working, already building the tools, and you, the person listening to this right now, wherever you are, whatever you were doing before you pressed play, are part of this story, not as a passive observer, as a member of the species that is asking the question, as one of the minds through which the universe is attempting, in its slow and improbable way, to know itself. The horrifying journey to Proxima Centauri is not primarily a journey across space. It is a journey across ignorance, a journey from not knowing to knowing, from assumption to evidence, from the ancient, aching question of whether we are alone, asked by every generation that has ever looked up at a sky full of stars to an answer. That answer is coming, and when it arrives in a spectrum, in a data file, in a quiet moment, in an observatory somewhere on this small blue world, it will arrive for all of us, every person who ever wondered, every child who ever asked why the stars are there, every scientist who ever spent a career pointing instruments at the sky and waiting patiently and stubbornly for the universe to speak. The universe is not silent because it has nothing to say. It is silent because we are still learning to listen, but we are learning. And 4.24 light-years away, in the faint red light of the nearest star, the answer waits. It has always been waiting. And if you think the journey to Proxima Centauri sounds terrifying, wait until you find out what the trip itself would do to us. That video is on your screen right now. Trust me, you won't sleep after this one either.